Hello, welcome to the 2.2 notes. These notes are all about defining the derivative of a function. Here is our definition of a derivative. The derivative of the function f with respect to the variable x is the functions whose value at x is f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x over h. Or you could say the derivative of at a, so f prime of a, equals the limit as x approaches a of f of x minus f of a all over x minus a. Go ahead and make an observation of this. You can pause this if you want to. This works provided the limit exists. So you might notice that these two notations right here look familiar. And that's because the instantaneous rate of change at a point and the derivative at that point are the same thing. And so a lot of times that phrase, instantaneous rate of change and derivative, can be used simultaneously. They mean the exact same thing. The difference is that the instantaneous rate of change is always going to be at a specific place. The derivative is just going to give you a function to help you find the instantaneous rate of change. So the derivative can be a function, while the instantaneous rate of change is always going to be like a value. And so we'll understand more of that as we go on. But there are some common notations for derivatives, and so some of the things that might not have been familiar to you as I just showed you this are these two notations, f prime of x and f of a. And so we are just learning new notations to talk about derivatives. So one of them is f prime of x, and the way that you say that is f prime of x, and that means basically the derivative at x. This is another one, dy over dx. This gets really popular as the year goes on, but the way that you say that is the derivative of y with respect to x. So you'll see this, like if you ever see this notation, this value up here, the y, is always going to be the dependent variable, and then x is always going to be the independent variable. So like you would have like a function equals y equals 2x plus 1. That's what I mean. Like y is the dependent, x is the independent. Y prime, that's what this one is. It's called y prime. Another one is d over dx of f of x, and this just means the derivative of f prime of x. And those four ones are the ones that we're going to use in calculus. I'm going to try to like switch them around so you get used to seeing different ones, that if you see it say find y prime, you know that that means find the derivative. This is a notation. I honestly don't even really know what this one means, but I think you use this one in physics. So this one's not common, but like this is, if you ever saw this in physics, like that's what that means. It's not common. I won't put it like on a test or a quiz or anything, but that's one that like you use if you're applying your calculus to like other sciences and things like that. So those are the common notations, and yeah, we're just going to use them as much as we can. So let's look at our first example right here. Sorry, sometimes this, you guys probably know this, but it doesn't copy over. So this one says example 2. I don't know if we had an example 1, but let's just pretend we did. This one says find the derivative of f of x equaling x squared minus 12 at x equals 4. And so what we'll do for this, if we're finding the derivative, is we're going to use this long definition of derivative that we saw earlier, which was f prime of x equals, and just like when we were finding the instantaneous rate of change, you can choose either of these two notations to use. I'm going to use the first one for this first problem, and then I'm going to use the second one. But we're trying to find the derivative of f prime of x and then at 4. So we're going to use this definition, the limit as h approaches 0 of f of x plus h minus f of x over h. So the first thing is we are trying to find the derivative at 4. If it tells us where we're trying to find the derivative, we can go ahead and use that. We're not always going to be told where to find the derivative. The derivative is the function that helps us find the instantaneous rate of change, and sometimes we'll know where we're finding it. Sometimes we'll just need a general equation so that if we do know where we're finding it, we'll have it. So specifically though, we're trying to find the limit at 4. So I'm going to plug in a 4 everywhere I see a x. So I'm trying to find the derivative at 4. The limit as h approaches 0 of f of 4 plus h minus f of 4 all over h. And we're going to go about solving this the way that we solved problems yesterday. So I'm going to take this function and I am going to plug in, I'm going to use function notation. I'm going to plug in 4 plus h in for x. So I'm going to go up to this up here, x squared minus 12, and I'm going to do 4 plus h squared minus 12 because that is f of 4 plus h. And then I'll do minus f of 4. So I'm just going to plug in 4 here for x. And then put that all over h, and then I will simplify. So if I were to plug in 0 right now, because I do have a limit, if I were to plug in 0 right now, I would get indeterminate form. I would get 0 over 0. So I'm going to have to simplify, maybe do some distribution to kind of figure out what this value is. So I'm going to go ahead and clean up what I can. So I'm not going to touch this first function. But 4 squared is 16, 16 minus 12 is 4. So I know that I'm going to have a minus 4 here. And then next what I'm going to do is I am going to distribute 4 plus h squared. So I'll write it out first because it says 4 plus h squared. So that means 4 plus h times 4 plus h minus 12. And then all of that will be minus 4 all over h. Now I'll actually distribute, so I'll get 4 times 4 is 16, 4 times h is 4h, this h times 4 is 4h, and then h times h is h squared, and then I don't really need the parentheses anymore, so I'll have 16 plus 4h plus 4h plus h squared minus 12 minus 4. Then I will simplify that numerator, and I will get 16 minus 12 minus 4 equals 0, because 16 minus 12 is 4, 4 minus 4 is 0, and then I'll have 4h plus 4h is 8h plus h squared all over h. And I still can't plug in 0 because, one, I haven't canceled out anything. So if you haven't canceled out, it's not all of a sudden going to work. I mean, I've canceled out the 16, but I haven't canceled out any factors that are giving me a reason to do 0 divided by 0. So what I'm going to do now is I am going to factor, because if you notice there's an h and 8h and h squared, so I'll be left with 8 plus h all over h. These h's cancel out, so I've canceled out a factor, and that factor was making me divide by 0. And so all I'll have left is 8 plus h, and now I can just like evaluate my limit with direct substitution. So if I do 8 plus 0, I will get 8. And that is the derivative at 4, aka the instantaneous rate of change of this function at 4. So we're going to go on to another one. This other one we're going to use the other derivative definition just so we can get practice doing both. So this one says find the derivative of f of x equals the square root of x. And it doesn't tell us where we want to find the derivative. It just tells us to find the derivative. And so this function that we're using is going to be the derivative. We're just not finding it at a specific place. But if later it told us find the derivative of f of x at 3 or at 4 or 9, we would use the derivative function that we get to find that. And so I'm going to use this definition here. F prime of a equals f of x minus f of a all over x minus a. And I'm going to go ahead. There's nothing to put in for a because, again, we're not finding the derivative at a specific place. So I'm just going to kind of go for it. And I'm going to start using function notation. So f prime of a is going to equal, so I'll have the square root of x because f of x is the square root of x, and then f of a is going to be the square root of a all over x minus a. Oh, and I forgot the limit part. So I forgot the limit part for both of here. So if you want to find the derivative, you have to find the limit as x approaches a of these functions. So if I were to plug in a right now, I would get 0 over 0. And so I have to do some more steps. And notice that we have square roots here. And so when I have square roots and I get indeterminate form, what I do is I will rationalize. And so I'm going to multiply the numerator by x plus a. And I'm also going to multiply the denominator by x, the square root of x plus a. And so I'm going to get the limit as x approaches a of the square root of x minus a, the square root of x minus the square root of a times the square root of x plus the square root of a, all over x minus a, the square root of x plus the square root of a. I'm only going to distribute the multiplication where there's square roots involved in both factors. So that will give me the square root of x times the square root of x is just x. The square root of x times the square root of a is the square root of xa. The square root of negative square root of a times x is minus xa, and then the square root of a times the square root of a with a minus is minus a. So this is what I'll have on the numerator. The denominator I'm going to keep how it is. I'm going to simplify the numerator, and those middle terms cancel out because they're the opposite of each other, so I'll have x minus a all over x minus a times the square root of x plus the square root of a. These two cancel out, so I've canceled out a factor, which gives me good hope that I'm almost done with this problem once you cancel out a factor, because I canceled out the reason why I was dividing by 0. And then I'm going to just plug in a. So I'm going to plug in a for x. So I'll get the square root of a plus the square root of a, and that equals 1. Square root of a plus the square root of a is 2 square root of a. And that's our answer. So that's our derivative of this function. Also, you could write the derivative is 1 divided by 2 square root of x. It doesn't really actually matter which variable you use at this point, but that is the derivative. And so we're just finding the derivative, not at a specific point, but just finding the derivative. So this last example says use the derivative of f of x equals x squared plus x to find the instantaneous rate of change at x equals 0, x equals 1, and x equals 2. So this is an example of why it's helpful to find the derivative just like the formula, the function, rather than finding it at a specific point, because then you have the formula and you can go ahead and use it for like 0, 1, and 2. So I'm going to use the original derivative one, the one that we used first. This one tends to be a little bit more, it's not necessarily easy, but I feel like you see it more often, so that's why I'm just using this one first. And I'm not going to plug in 0, 1, or 2 because I'd be doing this long problem 3 times. So I'm just going to go ahead and use function notation to start evaluating this derivative. So I'm going to plug in x plus h into x squared plus x, and so that will give me, it's going to look a little messy, but x plus h squared minus x plus h. So if you're getting confused on what I'm doing f of x plus h. And I'm just like plugging it in here. So I'm doing like x plus h squared and then plus x plus h. So anywhere I saw an x, I'm just replacing it with x plus h. And then f of x is just x squared plus x. But remember, you're subtracting that whole function. And so put it in parentheses. You're not just subtracting x squared, you're subtracting x squared and x. So that's what I'll have there. And I will start cleaning some things up. I need to do x plus h squared, and I can kind of do that in my head, but basically I'm doing x plus h times x plus h, and so that will give me x squared plus xh plus xh plus h squared, and then I will subtract that part by, I'm going to distribute this -1, so I'll have minus x minus h, and then I will also distribute this negative over here. So I'm just kind of cleaning this up. Just really take your time with this because it's easy to make mistakes. But you kind of know if you're making a mistake at the end, if whether you can cancel out an h or not. And if you can't cancel out an h, you probably did something wrong. So at this point, I have x squared. I'm going to clean up what's in the parentheses. I'll have 2x plus h squared minus x minus h. And then from outside the parentheses, I had minus x squared minus x. And now I'm going to cancel out anything that I can cancel out. So if I go through this, I can cancel out these x squareds because I have x squared minus x squared. And I can also cancel out the x's. And that's perfect because that means what I'm going to do next will actually work. Because I'll have 2xh plus h squared minus h all over h. And if you look at that, I should have... Sorry, it's just like very easy to make mistakes here. Okay, we're just going to keep going. I think it will work. Okay, so then this equals, I'm going to pull out this h, and I'll get 2x plus h minus 1. Oh yeah, this works. Okay. Still having the limit as h approaches 0. These h's will cancel out, and I'll get the limit as h approaches 0 of 2x plus h minus 1. And then at this point, there's like no division that could possibly happen by 0, so I can go ahead and plug in 0, and I'll get 2x minus 1. And that is the derivative. So that is f prime of x. F prime of x equals 2x minus 1. So that was the first half of this problem. Now I have to find the derivative at x equals 1, or x equals 0, x equals 1, and x equals 2. And I realized I didn't really leave myself much room, but I'm just going to put it right here. So that is the formula that will help me find the instantaneous rate of change. So I'm going to do find it at 0. So I'm going to find f prime of 0. And then I just plug that into that equation. So I'll do 2 times 0 minus 1, and that equals -1. So that's the instantaneous rate of change at 0, or the derivative at 0. You can interchange those phrases. F prime of 1 equals 2 times 1 minus 1, which 2 times 1 is 2, 2 minus 1 is 1. So f prime of 1 is 1, and then f of 2 equals 2 times 2 minus 1. 2 times 2 is 4, 4 minus 1 is 3. So f prime of 2 is 3. So that is the first half of what we're doing today. Now for the second half, and I think I assigned this homework in 2 pieces, so you might be at a stopping point at this point. But now we're going to go on to just like an additional step that is asked very frequently in calculus. And so first we're going to review some Algebra 1 questions. So I just want you to take a break, try to do this one. So this one says, example 2, find the equation of the line with a slope of 4 that goes through points 8 and -9. So this has nothing to do with calculus, just so you know. So we want to find the equation of a line. The equation of the line that we're most familiar with is y equals mx plus b, where m is our slope and b is our y-intercept. And a lot of you guys love using that one, but I want to encourage you to kind of open up your eyes for the other formulas. So the other formulas are standard form, which is kind of helpful. So standard form, ax plus by equals c. A, b, and c are just constants, so it doesn't really tell you anything right away, standard form, but it is good for writing equations if you were given like a word problem. But the last one is slope form. So it's y minus y1 equals m times x minus x1. And this is called point slope form. And m is our slope, and then x1, y1 is some point on the line. Some point on line. And so if I go back through this information, it says find the equation of a line with a slope of 4, so that's m, and that goes through this point 8, -9. So we have an x1 and a y1. And so yes, you could use slope-intercept form to find this formula. You just have to solve for b, but you could also use point-slope form because you have all the information you need to write this in point-slope form. So all you would do is you would do y minus y1 is -9 equals m is 4 times x minus 8. And then y minus, like subtracting a negative just gives us plus. We'll get y equals 9 equals 4 times x minus 8. And that is our answer. And so I just like personally find that easier to do than slope-intercept form. And for the problems that we're going to do, I think it will save you a lot of time to not use slope-intercept form. So we're going to do a little bit more review, but this is review of calculus stuff. So this says the derivative is just the slope of the tangent at a specific point. So if you remember a couple days ago, we said the instantaneous rate of change is the slope of the tangent. Well, the derivative is the instantaneous rate of change, so the derivative is the slope of the tangent at a specific point. And so if you look at this function right here, this is the function f of x equals x squared. We're not going to do all this work. I'm just going to tell you this. The derivative of x squared is 2x. And so this is the equation that gives us the slope of the tangent because it's the derivative. So let's say specifically that we want to find the derivative at 2. We want to find the slope of the tangent at 2. I would just plug that into the equation, and I would get 4. But if you guys want to go over here and look at this graph, if I were to draw a tangent line, and it's hard to draw a tangent line, so you're just going to do your very best to draw it. I'm going to draw it as best as I possibly can. Tangent line, just remember it hits the graph at one point. And if I were to find the slope from, let's say, here to here, because those are my 2 points that hit on corners, the slope formula is the change of y over the change in x. So I go up 4, 2, 3, 4, and then I go over, I think I go over 1. Oh, sorry, that's not up 4, that's up 2, because we're counting by 2. So I go up 2, I'm going to go over 1. This is, if you look at the scale. and I get the slope is 2. Oh wait, I should be getting the slope is 4 because, sorry, I'm not going over 1, I'm going to half. I'm just not reading my scale right. Sorry about that. Okay, 2 over 0.5. So I'm just trying to show you that these things, the formula, that's just like an estimate of the slope of the tangent, but that goes with the derivative. So I want you to just see that those are the same thing. And so we know how to find the slope of the tangent line, right? Because that's just the derivative. What if we found the equation of the tangent line rather than just the slope? So we want to find the equation. If I go back up, we would want to find the equation of that line right there. So I have some things that kind of got moved around on this function, so just ignore where it says example 2. We don't really need this. But we're going to revisit the last example. So if we're looking at this example, find the equation of the line tangent to x equals 2. If f of x equals x squared, that was our function, and f prime of x equals 2x, that's what we figured out on the last page. Sorry, that should just be moved there. And f prime of 2 equals 4. So if we want to find the slope of the tangent line, this is the formula we're going to use. We're going to do y minus y1 equals m times x minus x1. That's the formula we're going to use to find this. And we already know what the slope is. So the two pieces of information we need to know here is the slope, and we need to know a point on that tangent line. So we're using the example above. The picture didn't copy over when I moved things to Notability, but that's okay. Other notations you guys might see for writing the slope of the tangent line is this, because f prime of a just means the derivative. So sometimes you might see that, but just want you to remember that the slope is the derivative. And so we know that based on the last page that we showed you, that at 2, if we're trying to find the equation of the tangent line at 2, the slope is 4. And so I'm going to go into my equation, and I know that in my equation, 4 is my slope. So I can go ahead and plug that in right there. But now we also need a point on the line. So if I go back up here, I have this point on the line because this is where it started. It's 2, 4. And this point is on the tangent line, and it's also on the function, the original function, the function x squared. And so I can pull from that function anytime I need to figure out, because the tangent line like has a point on the original function. This one's at 2, 4. So that's my point on the line. It's 2, 4. And so my equation is going to be y minus 4 equals 4 times x minus 2, and that is the equation of this line up here. So we're going to do a couple more examples. So we're going to do one with this one. So this graph that you're seeing right over here, this is the function f of x equals 1 over x. And we are going to be asked to find the equation of the line tangent to x equals -1. So we are concerned about the equation, and I'm going to just estimate drawing a tangent line, and we'll talk more about how we can draw a good tangent line later. But it's going to look something like this. It's never going to be perfect when you're just like sketching it yourself. Sorry, I'm going to do that again. But that is kind of an estimate of the tangent line right there. And so I'm going to give you some information because I don't want us to have to do all of this, but the derivative, if we use that long derivative method, we would get this. The derivative is -1 over x squared, and if I were to plug in -1 there, I would get the derivative at -1. So I'll do -1 over -1 squared, and that's going to equal -1. And so right off the bat, when we're writing the equation of this tangent line, let's say that we use this notation right here, we automatically know that f prime of a is -1 because we know the slope of the tangent is -1 because that's the derivative. So we already know that piece of information. We also already know that we are trying to find the slope of the tangent line at x equals -1. So we know the x value we're working with is -1. So I'm going to go ahead and plug in -1 as well, because we know that we're trying to find the slope of the tangent line at -1. And then we just need to figure out, okay, well, what's that point right there? That point, if you look at the graph, it's -1, -1. And if you weren't able to figure that out by just looking at the graph, well, that point is shared by the original function and it's shared by the tangent line. And so I also could have just taken f of x equals 1 over x, and I could have plugged in -1 here, and that would have given me -1. So my final answer is 1 minus -1 equals -1 x minus -1. I just got to clean this up, and I'll get f plus 1 equals -1 and x plus 1. And that's our answer right here. So again, I got that point because I looked at the graph. That's the that's like my x1, y1 point. But I also could have gotten it from looking at the equation. So we're going to, I think, we'll do 2 more examples real quick. And then we'll do one more graphically, and then we'll do another one without the graph. So, oh no. Okay, we're just not going to do the other one graphically because it's not on this piece of paper, but that's okay. So this one says find the line, example 5 says find the equation of the line tangent to x equals 3 when f of x equals negative 2x squared. So if we want to find the equation of the tangent line, we need two things. Again, we need, I'm just using different notations to kind of help us learn, but we need the slope of tangent, which is the derivative, and then the other thing we need is a point on our function, and this point is shared by the tangent line and OG function. So let's go ahead and do the easy part first. Let's go ahead and figure out what our point is going to be. Well, this tangent line is at x equals 3, so we already know that the value of the x value is going to be 3. Then I just need to find my y value that goes with this, and so I can just use the original function because I know it's going to be shared by both, and I'm going to do negative 2 times 3 squared, and that equals negative 2 times 9, and that equals negative 18. So I already know one part of my problem, like I know that my equation is that this 1 point on the line is going to be 3, negative 18. Now I'm going to go and do the harder part, which is I need to find the slope now, and the slope is the derivative. So I need to find the derivative of negative 2x squared at 3. And so I'm going to use, I can use either of the derivative formulas. You can use whatever one you're comfortable with. So I'm going to use this one right here just to get more practice with it. And I'm specifically trying to find the derivative at 3. And so I'm going to plug in, sorry, I'm just going to put a here, x equals 3, or this just means like a equals 3. So I don't need to plug that in for x. The thing that changes in these problems is always either a in this notation or x in the other notation. So what I'm going to do here is I'm going to find the limit as x approaches 3 of f of x minus f of 3 over x minus 3. And I can just go ahead and start plugging things in. So f of x is negative 2x squared minus, then I just plug in 3 into that function, so I'll get negative 2, 3 squared all over x minus 3, and I will start cleaning this up. So I'll get the limit as x approaches 3 of negative 2x squared minus, that'll be 9, so I'll have 9 times negative 18, so it'll basically be my negative 2x squared minus negative 18 equals x minus 3. This simplifies to a negative 2x squared plus 18. I gotta cancel out a factor if I want this to work. So I am going to take out the greatest common factor, which is negative 2. So I'll have x squared minus 9 all over x minus 3, and then I'll get the limit as x approaches 3 of negative 2. I'm going to factor that. I'll have x minus 3, x plus 3, all over x minus 3, and then these will cancel out. And I'll get the limit as x approaches 3 of negative 2 times x plus 3, and I can go ahead and plug in 3 now. I'll get negative 2 times 6, which equals negative 12, and that's the slope of the tangent line. So now I can go ahead and put everything together. I got to put it in my equation, so I'm going to have y minus negative 18, because that was the y1 value, equals negative 12 is our slope, times x minus 3, and if I clean that up, I'll have y plus 18 equals negative 12 times x minus 3. And that is the answer to that question. So that's the slope of the tangent line at x equals 3. So thanks for watching.